Guys, I would like to make some acknowledgement to these bodies because all these resources, all this information picked up from these areas. Now, I would like to cover two key areas, two key highlights. One of them is risk mitigations. Risk mitigation associated with handling electricity. Number one, you can get electrocuted by using step and touch voltages. Number two, I will have an induced voltage and then I could get explosion. This risk mitigations against electric shock and explosive. And the second key highlight is reliable operation and protection of the system, because you always want your adequate operation. You want to be able to isolate the fault, and you want to be able to avoid any blackout. All this can be done if we properly use our earthing system or our planet Earth. To take you through a history that I always find very fascinating, earthing system, it's not only from electric point of view, it gives us, number one, this, they say that's a New York before or after, give us shelter. Guys, maybe this is animated. However, this, I worked on it. This is in Western Sydney, as you can see, between 1997 and 2005, the growth in populations. Northwest, also in Western Sydney, between the same 2 years. You can see that we developed too fast to occupy our planet. By developing too fast to occupy our planet, we need to make sure that we always maintain a clean environment, a safe environment, and the most important element is safety. You don't want any explosion. You don't want any electric shock. Earthing system, for most of you, it might be a surprise. It started in 1800s. In 1800, they first introduced the telegraph. They used to send signals. This is good for communications. They used to send signals and they return it back in 2 wires. The 2 wires are running parallel to each other. They cause interference. So that led them to put more repeaters. The more repeaters they put, cost more money, and the maintenance goes high. So what they done, Mr. Carr in 1820, they proved that they can use the earth as a return path. So if we inject an earth rod into the ground deep enough, we will have a clear return path. Change the entire design system. By the way, guys, I read some article that in the World War, they used this technique to communicate. So no one can, because the earth, you cannot get the signal return from the earth. They cannot spy on them properly. So after this history, they introduced first into electricity is known as a single wire earth return. So instead, if you have a single phase, instead of sending 2 wires, you send 1 wire, take the power and let the earth return it back. After this, we introduced in early 19th century, 20th century, 1900, we introduced the electric machine. The electric machine caused fatality because of the magnetic field, and the unbalance caused explosion and fatality. So to avoid all these issues, after a thorough investigation, they found to have a safe and reliable electric machine, to have a safe and reliable system from a lighting perspective, to have a safe and reliable system for power network, you must have an earthing system. Earthing system, it's our ground. So the ground, it's not only an area where we physically build on it or stand on it, or we put our transmission line or a substation or a power station. No, it's actually an element. Like when I say it's a conductor, it's like when I say it's a transformer, like when I say it's a transistor, it's a diode, it's a part of it, similar. You need all this to make a switch power supply, but to get the electricity, you need the earth as a solid part. Now, this will show you why do I need earthing system. Why do I need earthing system? For number one is I need to control, you will see later on, that without a proper earthing system, I cannot control the earth's potential rise. A lot of people, when I talk to them and I tell them that if you are walking on the street next to a high voltage substation or tower, there is a risk of you get electricity. You can get electric shock just by walking by. Touching structure nearby a high voltage infrastructure, you can get electrocuted, especially for those who has kids. You will see now, a human body for us, they consider it to be 1,000 ohm. For babies, no. So they have to be very, very careful. Also, to provide path for fault return current. The current always has to go back to the source where it exits. So when there's a fault, for the current to go through, for those who are studying electrical engineer, they know we need to close the loop. If you don't have a closed loop, so it must go back. If this resistance, guys, you inject 1,000 ampere, if this resistance in the ground, it's high, you'll have a massive voltage. Ohm's law always prevail. V, it's equal IR. So that's why I need to design an earthing system that made of a soil and a conductor properly to make sure my return pass will not cause any high voltage or high potential along the way that could cause fatality. We also designed the single wire. The earthing system is required for the single wire earth return, the one that we discussed before, when we send one phase out and let the second comes back to the ground. One of the most important that we're going to spend some time is a step and touch voltage, and at the end, a lightning. You want to make sure when a lightning strike, guys, when you talk about lightning, you're talking about maybe 100 kiloamps. 100 kiloampere, it's a massive power. It's not small. It's hitting your building. It's hitting your high voltage infrastructure, your communication, telecommunication line. You need to be able to actually design a proper earthing system to absorb this massive energy. The next couple of slides showed the intensive of standard. By the way, all utility, all type of buildings, pipelines, communication, telecommunication, high voltage, low voltage, all standard required earthing system. All standard. That's why, if you can see, I put all the standard to show you the intense and the acknowledgement of this topic. So it's not our planet. It's not just a place where we physically sit on it. It will give us a proper and a safe environment for us to work. Before we go in, I would like to identify what's a high voltage infrastructure. High voltage, guys, it's worldwide been agreed. Any voltage above 1,000 volt AC or a 1,500 volt equal to 1,500 and above on the DC. And these days, you will see later on, these days that power stations, transmission line, substation, high voltage distribution line, and high voltage customers, they all located in a close proximity to us. You'll be surprised when you are walking. Are you walking next to high voltage infrastructure, or are you walking next to a house? Look, guys, at this. This is a real scenario based on a project that we've done before. That's a substation. That's a high voltage infrastructure that, depending on the location of the substation, this will attract lightning strike. This will attract high voltage fault. This will attract. This is another substation. It's a substation. Next to it, there's a house. That's a substation. That's a house. So people walking on the lawn in front of it, if the utility didn't do a proper design, God forbidden, kids running or people, elderly, they they have a chance to get electrocuted by step voltage, which is, you will see what's a step voltage, or touching anything nearby. So when it comes to human safety, we've been talking about step and touch voltage. What's a step and touch voltage? Step, if you're touching, number one, what's a voltage? Voltage is the difference in potential between 2 points. So if I am walking on the footpath and my legs at different potential, that's the voltage across my body. If I'm touching a fence, or if I'm touching anything that have a different potential than my feet, I will have a different potential between my hand and my feet. This is same at a farm. For the cows and the animals, there are more risk when it comes to step and touch voltage. Look, guys, at this lady that she's walking. Maybe she doesn't know. Maybe if the system in here, it's not properly designed, she's at risk to get high voltage or high current going through her body under fault conditions. One of the most important and critical, they call it in many countries, it's a black art, the earthing system, because you are designing, you don't know what's underground. We try our best to investigate our ground by injecting voltage and a current, and I'll show you what method, the most popular method that will be used for the system. So what will happen, guys, when you have a current goes into the ground, Ohm's law, the earth potential rise will be equal to the earth grid current multiplied by the Rg, which is the grid current. This Rg, it's made of the soil of our earth at this location, plus or in relation to our electrode. And depending on your resistance, depending on the resistance of your system, your voltage will be determined. Is it high voltage, low voltage? When you inject 10 ampere into 1 volt, it will give you 10 volt. If you inject 10 ampere into 100 volt, it will give you 1000 volt. 10 ampere into 100 ohm will give you 10,000. 1000 volt. 1000 volt, you know, your body might not withstand it. You will see now what will happen. Now, to ensure our human body, they've done a lot of study. Our body can withstand voltage with small period of time. For example, if your clearance time, what we mean by clearance time, the time to isolate the fault, if it's a small, the smaller, the higher the voltage I can tolerate. The higher the voltage I can tolerate. So this is very critical. Now, for us to have a protection system, you will see later on, that also the time required for the current to trip, to isolate, depend on your earthing system. So even for a protection that give you a reliable network, if you don't have a proper earthing system, your protection time will go up. If your protection time goes up, the clearance time, you are jeopardizing the safety of everyone around you. Your earthing system, the resistance of your earthing system govern the actual step and touch voltages. So there is an allowable limit that will be governed by human body and the clearance time and the soil resistivity. The actual soil earthing system govern the actual step and touch voltages. Now, all this information, guys, everything conductive make our earthing system, including wet timber poles. You have to be very careful. Wet timber poles, they're conductive because they wet. During rain, you have water embedded inside them. It will drive down their resistance. Inside the substation, every single steel it's made of considered part of your earthing system. If it's bonded or not bonded, if it's bonded, better. Why? Because you put it at the same potential level. If it's not bonded, it will cause a major issue. Every single pole, transmission line pole, it's formed part of the earthing system because worldwide they have an overhead earth wire system. So for a safety purpose, for a safety and operation purpose, we must make sure everything is bonded to the ground. Everything. If you walk inside a substation, you will see this is known as an earth mat. When you expect an operator to open and close high voltage system, they always put an earth mat. Earthing, this earth mat in here will be touching the same potentials to make sure that you are standing on the same potential. So even if this machine, it's at 1000 volt and your feet is at 990 volt, your voltage is 10 volt, which is make you safe. Now, from all this, we need to understand the soil resistivity. How do you measure the soil resistivity? Is by injecting current and a measuring voltage. This is known as a Wenner method. This Wenner method, the bigger you go out, the deeper the current will goes in. You need to go into the soil resistivity, check, do you have a low soil resistivity on top or on the bottom? Because you want to know, do you have to drive your electrode down into the ground deep? Maybe in the ground, there is marble. You will see now, there is a high soil resistivity. Then you will take your earthing system horizontally. You then take it deep into the ground. A lot of standard talked about human safety, human body. By the way, our resistance in a human is based on your skin. Break your skin, your resistance, because our human body is made of water, it will be very low. That's why if you have any broken skin, you have a higher chance of permanent damage. The skin is what causes your resistivity to be high. There is European standard, American standard, Australian standard, Middle East, all of them revolve around almost the same, except the American distinguish between two types of people. Personnel, 50 kilogram and 70 kilogram. They said inside a substation, you must use 70 kilogram equations. You are allowed inside the substation. Outside the substation, you only allowed to use an equation of 50 kilogram because this are more vulnerable. You will see more vulnerable. So when it comes to my step and touch voltages, when it comes to step and touch voltages, I need to define my allowable safety limit. The allowable safety limit depends on two elements: soil resistivity, clearance time. With the American IEEE standard, I need to distinguish between two personnel, 70 kilogram and a 50 kilogram personnel. And you will see why. They say that the bigger the body, the higher can tolerate. Inside your substation, you don't allow kids to go in. Even if female or a short person or a small person is gonna go in, must wear safety shoes, must wear gloves, must wear vest. So must be protected. So this will give him an additional layer of protections. For those who are studying with us now, power system, guys, I put this slide to show you that we also use Thevenin's equivalent circuit in reality. People think that, hey, hold on a second, we finish our education, we don't use it. When I did my PhD, I used the superposition theorem as well. So this to show you that our Thevenin's circuit is between the hand and the feet. Our Thevenin's equivalent circuit exists between your hand and your feet to apply V Thevenin's and Z Thevenin's. To show you guys that if you studied the system, it will be very, very good. Now, in this system, they consider the human body is equal 1000 ohm. What I want to show you now is 50 kilogram and 70 kilogram. These are the approved, the acceptable equations. T represent the clearance time. This rho S is the soil resistivity of your surface. This is the soil resistivity. That's your clearance time. And these are 50 kilogram and a 70 kilogram personnel. Look, example, if I have a 5 millisecond, half a second clearance time under different soil resistivity, you have different allowable or touch voltages. So if you have a clay, the touch voltages is 173 volt under 500 millisecond clearance time. If you have a solid granite or gravel, you can go to thousands of volts. That's why if you ever go to a substation or power station, they put a gravels. They put it all gravel. Why? Because the soil resistivity of the gravel is very high. It will give you some sort of isolations. And the earth grid is usually made of either electrode. The earth grid usually made either single electrode or a combination of a mesh and electrode or mesh. If you have a very high soil resistivity, by the way, under the current standard, it's not recommended to have a high voltage infrastructure substation without having electrode, at least one or two. So they don't like to have only mesh. They like to have always an electrode driven down into the ground. So guys, what happens when you have an earth potential rise? When I have an electrode driven down, depending on the resistance of the electrode, that's also depending on your soil resistivity. That's your soil resistivity from the ground. You will determine your RG. This RG will determine your EPR. And look, guys, I run a couple of scenarios based on a hand calculation, based on a CDEX. By the way, CDEX is one of the most powerful software in earthing system. We installed 6-meter electrode. The cross-section area is 70 square mil. And look, guys, the resistance for a different values. If you have a clay, your resistance 7.99. If you have gravel, look at your resistance. 2,000, 5,000. So depend on your system. It's a very important to obtain the soil resistivity, then determine. Under standard, we are not allowed to commission a substation without having a resistance less than 1 ohm. You must imagine you have to drive this from 3,000 ohm, you have to drive it down to less than 1 ohm for you to be allowed to commission a substation. Because the substation, you have the voltage, the current is very high, the fault current. So when you have a very high, very high soil resistivity in the substation, we can use our transmission line, staff code overhead earth wire. And nowadays, by the way, it's a communication line. It's called optic fiber ground wire. When you have any fault into the ground, part of the current will goes into the ground, part of the current goes back into the overhead earth wire. Into the overhead earth wire, you have a stuff called mutual impedance, because they will have some sort of AC interference between the phase. You have an AC interference between the phase carrying the current, and you have a back EMF based on your physics. The current going through, guys, the current that goes through, he will have use your right hand rule. You have a magnetic field. The magnetic field will induce a voltage, opposite polarity on the overhead earth wire, and force the current to go through it. All this governed by a stuff known as a split factor. And this is what's a split factor. No. And we all know that the substation depends on the current that goes into this amount. Now, for a split factor, all these are important. To determine the split factor on top of the soil resistivity, what determinant is the layout and also the type of overhead earth wire. By the way, it's an optic ground wire. These days, because they want to communicate between the SCADA, between the protection of multiple substations, they use optic fiber. Why? Optic fiber has no interference problem. I don't have an interference problem at all because it's an optic fiber. It's a light that going through. the magnetic field has no impact whatsoever. So under the split factor, guys, we have to distinguish between two elements. One element is known as continuous overhead earth wire, one element known as broken overhead earth wire. When you have a broken overhead earth wire, create a dangerous zone. So we need to make sure that always I have a continuous overhead earth wire between my two substations. You will see what will happen when you go into the system. Now, the overhead earth wire, again, I put this equation because I know students, when they study, they finish education, they say, that's it, I'm done. This is the equation that they've been taught into the transmission line modeling. Into the transmission line modeling, the DE, depending on your soil resistivity, the geometric mean radius of your RG, all this is being determined and studied. So guys, when you finish your education, doesn't mean that's it, you're gonna close your book. If you wanna work in this domain, you will have to go back and open the book and revise again. Look what will happen under fault current. When I have a fault current, our substation earth grid will force the current to go back through the ground. That's why the current that goes into the ground, and I will have an EPR, earth potential rise, which is equal based on IG multiplied by RG. This RG depending on your earth grid system. That's the steel that putting into the ground. Now, part of it will goes back through the overhead earth wire. Part of it will goes back, remain into the overhead earth wire. If I have a substation without overhead earth wire, look what's going to happen. All the current will be goes back through the ground. So this system, a substation without an overhead earth wire, you must have a strong and proper design for your earthing system, because it will be on its own. If I have a transmission line and I have one fault at one pole, I have one wire drop down, part of it will goes down into the ground, part of it will goes back through the overhead earth wire. Imagine you live next to a pole. Under any fault, this pole, it's going to take current. It's going to take current into the ground. That's why every pole must have a design, must have an earthing system. Every single transmission pole, to make sure under fault condition, you will have a very low earth potential rise. Now, as you can see, everywhere I have earthing, everywhere. I put this scenario and I put the other scenario. One of them has no overhead earth wire, one of them has overhead earth wire. See, they put in here overhead earth wire. If you guys have a lightning strike without overhead earth wire, your light, your actual conductor might get damaged. So you need to have some sort of performance system. This is based on a lot of case studies. In overhead earth wire, if you design a proper overhead earth wire, will take 60 or 70% of your fault current. So imagine someone tell you, design this properly and will take up to 70%, sometimes more, of your fault current. If you have a cable screen, or earth continuity cable, this ECC earth continuity cable, because the cable screen is very close to your conductor, could be a couple of centimeters, the mutual impedance will be very high. This mutual impedance will force a current, will create like a vacuum. When the current hit the ground, it will vacuum through the cable screen, could be up to 90, 95, 96, 97%, depending on the soil resistivity around it. Now, these last few slides, I would like to show you that in reality, when it comes to system, it's good to know what's an MEN, main earth neutral system. The main earth neutral system, 100% utilize the current into the ground. You have a local common main earth neutral system. This uses the high voltage and low voltage earth grid. You have common main earth neutral system, use the cable screen. So it's very important, very critical to distinguish between this distribution system, because if I'm living next to one and I have kids playing around, I need to make sure that they have a proper design, because every single system for the MEN, for the LCMEN, local common main earthing system, or the common main earthing system, they completely have different. Each one of them has a completely different system. I need to make sure that it's been designed properly. The fault current will split only into the ground because it's open at the end. See this? Because it's open, I must have a closed loop for the current to flow. If it's open, the current will not going to flow back through here. All of it will go through this and cause me in here an EPR. If I have a common main earthing system, I connect this, and now under fault, could I have 90 or 95% returns. All this about the earthing system to show you, without our earth must be a solid part of our system, I cannot have a safe working environment. That's number one. Number two, protections. What's a protection? I still remember when I delivered the course at university, one of the famous questions I like to ask, why do you use protection to student? Why? Not to student, we do a training program. Why do you use protection? Number one, I need the protection to sense. I need the protection system to sense the fault. To sense the fault, and I need it. Why do I need to sense the fault? To isolate. Now, it's not only to isolate, I have a safety factor. I need to isolate as fast as possible. I needed to sense the fault. To sense the fault, the lower the resistance of your earthing system, it's a better sensing mechanism. In reality, I have two types of protection. I have a high fault protection, low fault protection. In the mine, they use an NER, neutral earth resistor, to make sure to lower the fault current, because what they will do is, that will be good for under the star of your transformer, they will install a resistor, NER resistor connected to ground. This will be made in series with the current going into the ground. They will hit this big resistor, which means they look at it as a high impedance. They lower the current. They lower the current. That's why they use it. And this equation, again, we learned it into many subjects at the university. Sequence component of your transmission line, and this ZF is your earth grid resistance. This is your, and also you have your zero sequence impedance. All this that we really learn in university, and if you pay attention to it, it will be very important, very critical for our work. Now, after I needed to sense the fault and I needed to isolate the fault. Why I needed to isolate the fault? Guys, our heat element that causes explosion, it's I squared R. I squared R, when I increase this current, it's very huge. Maybe 10 or 20 times the rated current. All the equipment that's been designed, it's been designed, if you look at your circuit breaker, your transformer, it's designed for additional current for a short period. 2, 3 seconds, 5 seconds, 1 minute. So what I have to do now, what I have to do is, I have to isolate the fault in a very clear and a fast way. And look, guys, the circuit breaker. The circuit breaker, the faster the current, the bigger the current. Look, if the current, it's exactly the same. This is, look, this is the same 10 times the rated current. It will not trip. If it's in here, if it's 10 to the 1, if you multiply it by 10, I need it to trip in this location. I needed to trip 100 millisecond, 200 millisecond, 80 millisecond. I wanted to trip very fast. If it tripped very fast, what does it do? We reduce the amount of energy caused by this fault. Remember, the energy, the electric energy is watt-hour. It's not the instantaneous power. That's very critical for us to determine. So our circuit breaker that taken this load, this massive, I needed to trip in a small amount. Also, if I go back and I recall my equation, back in regard to step time, the allowable touch voltage will increase if my clearance time increase. And all this will happen if I have an adequate earthing system. Without having an adequate earthing system, what's going to happen? Protection will take longer time to clear. I have a dangerous to my equipment. I have a high earth potential rise. And I have, on top of that, I have an issue. I have a major issue with my step and touch and maintain safe working environment. I did a job once in the industry. We had a high soil resistivity. We had to go get a permission to connect the entire town into the earth grid of the substation to lower the resistance and to make sure the EPR doesn't go above the allowable limit. Now, last item is your lightning. I want you to share with you guys this information for one reason. The lightning bright that you will see is a returning stroke, and look at the power of your lightning. Medium value of 24,000 ampere. 24,000 medium, could reach 100,000. What's the frequency? 100 kilohertz. If you have a conductor, what's a J omega L? So no longer have a resistance. You have some stuff called surge impedance. Surge impedance, don't tell me when the current hit, when the lightning hit a transmission line, it will go to the ground. It's not going through the wire. Why? Because the span of the wire has inductance. Inductance is J omega L. Omega is 2 pi F. F is 100 kilohertz. So we look at it like a 500 ohm. No. We'll go into the surge impedance of the ground. So when it comes to lightning, I have a lightning shield. And also, I will have a lightning performance. Lightning performance, if your lightning shield failed, the lightning performance will determine would it, I can put some sort of protections. After the shielding, after my direct lightning, I can put some devices. This for direct impact. This in here, I can put surge protection, lightning protection. It's a second protection line. And by the way, guys, everything, as you can see, cannot work without your famous earthing system. Everything. So all this, guys, it's been proven. We did a massive project a few years back. And the actual project, we physically went, we said, hold on, we want to go back extra mile, and we really want to physically establish this in line. We cannot go do the testing in reality, in real life all the time. So what we did is physically we built a mini transmission line. This is about 1.2, 1.4 meters. We put Sherry conductor that's been used for 66 and 33 kilovolt. And we physically built a mini earthing system. And what we've done is we went and we bought an AMAC. AMAC unit, it's an accredited unit that will physically, and what will happen is we inject current and we measure along the line. If you take it deep into the ground, what will happen along the way? On the rainy day, and the very dry day, and we tested and we got massive results based on this experiment. And that's why this experiment managed to publish, I think, about 25 journals based on all this work, not only in here, because of AC interference, because of soil resistivity, fault potential, all this information. To conclude our presentations, our planet Earth supports the electric development since 1800. Our planet Earth, it's not only the foundation, it's a play an important role. Guess what? I can remove a transmission line by making another one bigger. However, I cannot replace our Earth into the power system. I cannot replace the power Earth. Without an adequate earthing system, without studying the Earth, let me tell you guys, I spoke to one of my colleagues here in the industry earlier this year. They want to do a substation, but guess what? They cannot choose a site because it's a massive, it's a DC line, because of the electrodes. You have to have a proper earthing system. In many places, we have to relocate our substations because the cost of earthing system, it's a massive. Without earthing system, we cannot maintain the safety. You know, if you don't have an earthing system, you go to any factory warehouse that utilize electric machine, you will get electrocuted as soon as you touch it. Guys, inside the electric machine, 99% of the electric machine is the three-phase. The three-phase, under any unbalance, you have a zero current. The zero current will go into the body, magnetic field. The body is made of steel. Automatically, you have an induced voltage. You touch your electric machine, you become the path to Earth. And no protection without earthing system. Because like I said, there's a two type of protection. Number one, high fault current, low fault current. Both of them require earthing. How do you achieve low fault current? By putting in neutral earth resistor, NER system. And I think that's it for me. And I will leave if anyone has any questions.